In section 3.1, we learn how to calculate the formula mass for a compound, and we develop the concept of the mole. So earlier we defined the relative atomic mass of every kind of atom that's in the periodic table. How we did this was to assign a mass of exactly 12 AMU to a carbon-12 atom, by definition, and then we calculated the relative atomic weight for every other atom that's in the periodic table. Now I'm going to mention this several times, but it's worth noting that AMUs, atomic mass units, are very small and are not a particularly practical method of determining the amount of matter in an object. We can also define the formula mass of a compound. This is just simply the sum of the atomic masses of all the atoms that are present in the chemical formula of a substance. We call this the formula mass. So if I was asked to calculate the formula mass of this compound, C2H4, that is ethene, I would add together the mass of 2 carbon atoms and the mass of 4 hydrogen atoms. And so this is telling me that the mass of one C2H4 molecule is 28.054 AMUs. So this is what we call the formula mass, or in this case, it sometimes might be referred to as the molecular mass because it's relating to the mass of a molecule. The formula mass of an ionic compound is the mass of the smallest repeating unit of the formula unit. This is what we also know as the empirical formula. So it is the mass of the ratio of ions that gives us electrical neutrality. So barium sulfide has the formula BAS. So to calculate the formula mass of barium sulfide, we add together the mass of 1 barium and 1 sulfur. And then that gives us a mass of 169.39 AMU. And again, I'm just going to reiterate that atomic mass units are very small, so they're not an especially practical way of determining the amount of matter in a sample. So chemists need a more practical unit of mass to count the number of atoms or molecules in a sample. And in particular, we'd like to be working in grams because grams are kind of like what we can measure easily. So to allow us to do this, the concept of the mole was developed. And the mole is simply the number of carbon-12 atoms in exactly 12 grams of carbon-12. Now it turns out that this number is 6.022 by 10 to the 23 carbon-12 atoms. And we say that in 1 mole of anything, there is that number of particles. And this number is known as Avogadro's number. It's normally given the symbol uppercase N subscript uppercase A, and it represents the number of particles in a mole of something, just like in 1 dozen, there would be 12 particles. In 1 mole, there are 6.022 by 10 to the 23 particles. So Avogadro's number is useful because it allows us to convert between the number of moles of something and the number of particles. So just a sort of like cheesy example is we can calculate how many moles of donuts there are in a 24 box of donuts. Now, considering that in 1 mole there are 6.022 by 10 to the 23 donuts, 24 donuts is not going to be very many moles at all. So I'm expecting to get a very small number. So we recognize we want to convert between the number of particles, donuts in this case, and moles. So we're going to have to recall Avogadro's number. So that's where we're going to begin. So we're starting with 24 particles, which in this case are donuts. And so in order to turn this into moles, we're going to have to multiply by the conversion factor that will cancel particles and leave us with moles. And so for that reason, we want particles on the bottom line of our conversion factor and moles on the top. And what do we know? We know that for every 1 mole, there are 6.022 by 10 to the 23 particles. So particles will cancel out, and then we'll be left with moles. And we were anticipating a small number of moles because 24 is a lot less than 6.022 by 10 to the 23, and we got a tiny little number. So the relationship between moles and Avogadro's number and the number of particles can be summarized by this little diagram here. If I want to take moles and turn it into particles, I'm going to multiply by Avogadro's number. And if I want to take particles and turn it into moles, I'm going to multiply by 1 over Avogadro's number. So just reiterating, Avogadro's number is super useful as it serves as the conversion factor between moles and the number of particles. So as atoms have a fixed mass, a mole of a pure substance will always have the same mass. And that's really helpful. So one carbon-12 atom has a mass of 12 AMU, and by definition, a mole of carbon-12 atoms has a mass of, you guessed it, 12 grams. A single sodium atom has a mass of 22.99 AMU. A whole mole of sodium atoms weighs 22.99 grams. And so on and so forth for every atom in the periodic table. So a really useful observation is this, that 1 mole of an atom weighs an equivalent number of grams as the mass of 1 atom in AMU. So we can always get the mass of the atom in AMU from the periodic table, and that's just going to be the same as the mass of a mole of that atom in grams. So we give this mass a name. We say the mass of 1 mole of anything is called its molar mass. So the molar mass of carbon-12, for example, is 12 grams per mole. Often people will use an uppercase M as the symbol for molar mass. And you can always tell it's a molar mass they're referring to because molar masses always have units of grams over moles. So previously we calculated that barium sulfide has a formula mass of 169.39. We did this by adding together the mass of 1 barium and 1 sulfur. So that means we know that a whole mole of barium sulfide will have a mass of 169.39 grams, or more commonly people will say the molar mass of barium sulfide is 169.39 grams per mole. So sometimes calculating the formula mass for an ionic compound can be complicated because we use parentheses. So a good example of this is given in your text in example 3.2, where you're asked to calculate the formula mass of aluminum sulfate. And what we need to be mindful of is that the sulfate anion here is placed in parentheses, and then there's a 3 times multiplier outside. So when it comes time to calculate the mass of aluminum sulfate, we have to take into account that everything in parentheses needs to be multiplied by 3. So in order to calculate a formula mass for a compound, you're going to need a periodic table, and then you have to look up the masses of the relevant atoms. Once you've got that, you just got to not make a mistake in making sure you got the correct number of everything. So according to the formula, I've got 2 aluminums. Then I've got sulfate, but that is multiplied by 3. So just making sure that we've got everything accounted for is the key here. And here we are, 342.14 AMU. Some periodic tables will give masses to 2 decimal places, some will give to 3. Just use the values that you're given on your test or quiz. Here's another one. It says determine the molecular mass of the following compounds. So what I like to do is get a nice, easy to follow formula. So we've got 1, 2, 3, 4 carbons here. And then we've got 1, 2, 3, 5, and then another 3, 8 hydrogens. So this is going to be 4 times 12.01 plus 8 times 1.008. And I'm just getting those masses from the periodic table. So I'm going to put all of that into my calculator. 4 times 12.01 plus 8 times 1.008, and that gives me 56.10 AMU, and that's the mass of one molecule. Okay, for the next one, we're going to do the same thing, just make sure we add everything up correctly. 1, 2, 3, 4 carbons, and then 1, 2, 3, 4, 5, 6 hydrogens. So this one's going to be a little lighter. So 4 times 12.01 plus 6 times 1.008. Let's see what we get. And they got 54.09. And we always want to make sure we get units. Okay, and it looks like OpenStax agrees with me. They want 1 decimal place further, but that's fine. So it's a pretty simple leap to realize that 1 mole of a molecular compound will weigh an equivalent number of grams as the mass of 1 molecule in AMU. So if I was asked to calculate the molecular mass of water, I know that water contains 2 hydrogen atoms and 1 oxygen atom, so I'd have to add the mass together of 2 hydrogens and 1 oxygen. And this is the answer I get. So 1 water molecule weighs 18.02 AMU. What this means is that 1 mole of water weighs 18.02 grams, or more commonly people would say the molar mass of water is 18.02 grams per mole. Now, what's nice is that the molar mass can function as a conversion factor between the mass in grams and the number of moles. And you can see I've given the standard abbreviations or symbols for these quantities here. So this question asks, how many moles are there in 2.54 grams of water? So we need to recall this fact at the top, that it is the molar mass that functions as the conversion factor between the mass in grams and the number of moles. So we can go ahead and calculate the molar mass of water. So we've got 2 hydrogen atoms and 1 oxygen atom. So there's our molar mass of water. It's saying that in every 1 mole, there are 18.015 grams. So we're starting with 2.54 grams, and we're going to use this guy as a conversion factor. So hopefully you can see that we're going to need grams on the bottom line and moles on the top line if we want to cancel out grams and have moles remaining. So I know that in every 1 mole there are 18.015 grams of water. This will cancel out the grams when I multiply by this conversion factor, leaving me with moles, and I rounded my answer to 3 significant figures because the 2.54 has 3 significant figures. This answer makes sense because I've only got 2.54 grams, which is a lot less than 18, so I should have less than 1 mole of water. Okay, here's another one. We're going to do it in exactly the same way. It says, how many moles are there in 3.54 grams of calcium chloride? So I recognize that I want to go from grams into moles. So I need to use the molar mass as my conversion factor. So the very first thing I did was add together the mass of a calcium and the mass of 2 chlorines. I'm just getting those masses from the periodic table. So this is the mass in grams of 1 mole of calcium chloride. So now I can go ahead and calculate my number of moles. I'm starting with 3.54 grams, so I need to multiply by the conversion factor that cancels grams and leaves me with moles. And so for that reason, I'm putting the 110.984 grams on the bottom line. And you can see that when I multiply, grams cancels out and the only units that remain are moles. Now, there's about 111 grams in a whole mole of this compound, and I've only got 3.54 grams, so I must have a lot less than 1 mole. And when I do the math and I round off to 3 significant figures, sure enough, I have a lot less than 1 mole, as I would expect. So we can put all of the conversion factors that we've learned about so far together into the one diagram. So it's possible to convert between the number of particles of something and the number of moles of that thing using Avogadro's number. That was the first conversion factor that we learned about. And now we've just learned that we can convert between mass and moles using the molar mass. If I take moles and multiply it by the molar mass, I get grams. And if I take the grams of a substance and multiply it by 1 over the molar mass, I get moles. It's worth noticing, just to help keep your head straight, that whenever we're converting into moles, we expect to see a 1 on the top line of our conversion factor because it's always going to be 1 over Avogadro's number or 1 over the molar mass. So try to keep that in mind. It might help you avoid an error. Okay, so here is another example using the molar mass. It says, what is the mass of 3.20 moles of H2O2? So again, we're going to be converting between moles and grams. So I need to recall that the conversion factor that allows me to do this is the molar mass. And then I'm going to go ahead and calculate the molar mass, adding together the mass of 2 hydrogen atoms and 2 oxygen atoms. So now I want to calculate the mass, but I'm given the moles. So I'm going to need to multiply by the conversion factor that cancels moles and it leaves me with grams. So I know that there are 34.016 grams in every 1 mole. So by multiplying by this conversion factor, moles will cancel out, leaving me with grams. Now my answer here makes sense because in 1 mole there's about 34 grams and I've got a little over 3 moles, so 3 times 34 should give me a number that's a bit bigger than 100. And sure enough, what do I get? 109 grams. Note again, I rounded to 3 significant figures. Okay, so that concludes the video on section 3.1.